Okay, so another example. This is adamantine. The name itself says that uh, adamant means what? Adamant means very very stubborn, right? I mean, the people are adamant means they are reluctant to change. As a science student, especially a chemistry scholar, shouldn't be adamant because chemistry itself is the study of changes, the transformation. We must always we must build a mindset for accepting all the flaws, whether it is in science or in life. Okay, yes. So so this molecule is also reluctant to change because it is locked from all sides and it is three different chairs fused. Okay, and if you see, this is the basic unit of diamond. This is the kind of packing in diamond. Okay, carbon gets packed like this. Okay, it's not diamond actually. You know here here we have hydrogens. Okay, but in diamond, this is the kind of packing that carbon has. Carbon is connected tetrahedrally to other four carbons. But here there are, of course, hydrogens. Okay. Anyway, it is not much important for us at the moment. So here we can just type a note. Okay. So diamond like packing. Okay. So now we can go to our reaction. So another another point I want to mention is that how how we can draw an adamantine. Make a chair. Okay, so first draw a chair and then mark three bonds, three axial bonds, and after marking three axial bonds, then mark a common point here in the right middle of the three, and and uh, and attach all these bonds with the common point. Okay, so and attach this. Okay, then we can easily draw an adamantine. Okay, here this ketone, when we shine light, it will undergo homolytic cleavage. So we have an oxygen radical, and we can show our homolytic cleavage here. Okay, you can understand that it is a homolytic cleavage. Okay, so now there are two hydrogens in the gamma position. This is the alpha, this is the beta, and this is the gamma position, and there are two hydrogens, and both are equivalent. So this hydrogen will be abstracted. Okay, so you can just mark here. Okay, okay. It is as in the usual case. Okay, there is no much difference from that. Uh, so one hydrogen will be abstracted. So we have an OH and a methyl here. In this case, what will happen? McLafferty rearrangement or ring closing. So if McLafferty rearrangement is happening, okay, so if McLafferty is happening, then this is a bond. This is a bond which has to homolytically cleave. Then what will we get? Yeah, the ketone will not have any issues, but alkene have issues now. So this will be the alkene that if we are going through the McLafferty rearrangement, this will be the alkene that we will get. Okay, that you can understand that after the homolytic cleavage of this bond, there will be double bond here. Okay, in this bond. I hope you all remember the rules. So what is it? So this would be the double bond formed if it is going through McLafferty rearrangement. But uh, but this is a bridgehead. Okay, and this is a bridgehead. This is a bridgehead. This is a bridgehead. This is a bridgehead. All these are bridgeheads. So bridgehead shouldn't contain any double bond. Due to that, no reaction will proceed which end up in double bond at bridgehead carbon. Okay. Okay, so the bridgehead is where two rings got fused. Okay. Yeah, it is very simple. It cannot have an sp2 system in a fused ring because that's not geometrically feasible. So McLafferty rearrangement will violate all existing principles of chemistry. So in this case, the radicals will ring close. Okay, so the radicals will ring close like this, and the McLafferty rearrangement will not happen because it will end up in a product like this, which is not uh, according to the normal rules, or it is not possible. This common is not possible actually. That's why. Okay. So in this case, the radical should ring close, and yeah, in chemistry, all things are relative. The stability, the formation, and everything. So even if it is strained, even if it is strained reaction, the reaction will be proceeded because the other reaction, the alternative reaction, is not at all favored. Okay, okay. So you get this product. Here this will be the final product. Okay, now we can move into another example. So what happens in this case? In this case, the it will form biradical initially. Okay, biradical will be formed. So it can abstract a delta hydrogen. Okay, so this is alpha, this is beta, this is gamma, and this is the delta position, and there is a hydrogen here. Why it is abstracting delta hydrogen? Because there is no gamma hydrogen. There is no hydrogen in the gamma position. Also, the delta hydrogen is proximal proximal to the oxygen radical. So it will proceed in the usual way after abstraction. Okay, okay, we can look into that. Okay, so we can just make a note here. Okay, and then we can make in the next page. Okay, so we can go to the next page. Okay, so it recommends. Okay, that is the next step. It will ring close as in the usual cases. So it recombines, and when we are taking the delta hydrogen, we get a 5-membered ring. So this is usually when we take delta hydrogen, we get a 5-membered ring. Yeah. So we can just make a note here. When okay, so when we are taking delta hydrogen, 5-membered ring is formed. Okay. Okay. Yeah. So the stereochemistry, if we just fancy the stereochemistry here, there is only relative stereochemistry. Okay, each phenyl will be at the opposite sides, as indicated here. Yes, as we know, these bonds that I will mark here. Here there is this complete bond. So you may not. Okay. Okay. So here you can rotate this bond actually. Okay. I am just marking that this it can rotate. Okay. So as you know, these bonds can rotate to reach a stable conformation before ring closing. Okay, and end up in a less hindered product like this. The phenyl groups will be positioned in a in opposite positions. Okay, so there is only a relative stereochemistry. Okay, I just said it for it's not that much important. Okay, okay, so we can move into next example. Okay, so we have methyl here, and the benzophenone is also there, and we have got a conformational lock. Of course, we have hydrogens on the cyclohexane. You have to use it in the further steps actually. Now what happens? Okay. And what happens now when we shine light? Uh, here we have two pairs of gamma hydrogen. So this is the alpha, this is the beta, and this is the gamma position. So here we have two gamma positions, two gamma hydrogens. Okay. So you must note that, but both of them are actually the same. They are identical. So one among them will be abstracted. Okay, this hydrogen is axial and this is equatorial. So the oxygen radical will selectively take the axial hydrogen. Equatorial hydrogen is down right. Okay. Of course, the proximity of hydrogen atom plays a important role. Okay. So now the radical will enclosed, I think. Okay. Yeah. So the radicals will ring close like this. Just marking the arrows. Okay, so now we have the product. Okay. Okay, so that's it, and we can move into next example. Okay, now in the earlier cases, we started with an axial ketone. Okay, the ketone group was in the axial position. But in this case, we start with the equatorial ketone. Okay, rest all groups are same. Here the conformational lock is also there. Okay, so we have only changed the positions of methyl and benzophenone. Okay, so you can understand that. So what happens in this condition? Okay, so there is no gamma hydrogens to abstract actually. There is gamma hydrogens. These are this will be alpha, this will be beta. So so these are actually this carbon have gamma hydrogens, but those gamma hydrogens are miles apart for this oxygen radical to for this oxygen radical to abstract, because these are very far. These gamma hydrogens are very far when coupled to an oxy radical in the equatorial position. So oxy radical can't take these gamma hydrogens, this compound. Then what will proceed next? Okay, so there is no delta hydrogen also. There is no hydrogen. So anyway, it is more than this is the it is more miles apart from when compared to the gamma hydrogen. We don't want to think about that. Okay, so what is the way which is in front of this molecule? Okay, so it will arrange as normal NORRISH type 1 reaction, and form an acyl radical and an alkyl radical. Okay, so we can just mark here. Okay, normal NORRISH type 1 reaction will be followed because there is no other pathway. Okay, you can understand that. So, so that is the compound undergo NORRISH type 1 reaction. Now, this less stable acyl radical can abstract this hydrogen from this compound. Okay, so this hydrogen will be abstracted by the acyl radical, and a double bond will be created. Okay, I'm not making any arrows. You could understand, I think. So we will get these two products, and okay, this is the case when we start with the equatorial ketone. Okay, so in all these cases, whether it was the axial or equatorial ketone, we had the conformational lock. Now, what happens if we lack conformational lock? Okay, so it is very interesting to note what will happen if there is no conformational lock. Okay, so we can go into an example where there is no difference, but the conformational lock is not there. Okay, okay, here there is no conformational lock. So here there is no tertiary butyl. Okay, so can you think sometime that what will happen in this case? Okay, as we have mentioned in the earlier slides, this can reflect into this compound. Okay, so the axial will become the equatorial. Okay, and the equatorial will become the axial. Actually, I want to show the kinetics. Okay, how fast. So this goes to this product. Sorry, this goes to this compound. In I mean, I can just type here. Okay, so to this compound goes to this compound in 10 raised to 5 per second. So it is towards equatorial. Okay, this is more stable. That's why the forward reaction is it have a larger rate. So the right side compound is very stable. Now if we shine light, we have both forms are in the mixture. Anyway, these are in small amount, but both portions are there. This compound will be in the major share, but this compound will be also there. So when we shine light, if there is no conformational lock, okay, in this case, of course, there are hydrogens which is available, and in this case, it doesn't have delta or gamma hydrogen. It only have some only have some beta hydrogens. So, and it cannot be abstracted, the beta hydrogens will not be abstracted. So, this will be the beta hydrogens, but it will not be abstracted. So, this will, so it cannot be abstracted. So, type 1 reaction will be ensued as we have seen in the previous example. The normal NORRISH type 1 reaction will be followed in this case. Okay, so and in this compound, this will take, there is no problem, and this will take this hydrogen, and we will have two radicals, and it will bring close to finally forming this product. Okay, as we have seen in the earlier examples, as in the usual case, this product will be formed, and in this reaction also, the proceeding through normal NORRISH type 1 reaction, this will be formed. Okay, so this will be the minor product. Okay, this will be the minor product, and this will be the major product. Here, while we were starting, the left side molecule was minor. That is 10 raised to 5 per second means the right side was major. Okay, but when we come to the product, this one is the major and this is the minor. So miracle is happened at these steps. Okay, so I will mark the okay. So the miracle happened at these steps. Okay, here it is 10 raised to 7 per second, and here it is 10 raised to 8 per second. So this is more faster. Okay, and there is an equilibrium between these excited states. Okay, so everything at this stage will come back to the left side. Okay, this, and it will react from the left side. So this will be the major product. So that is why these reactions are having this product as a major and this product as a minor. Okay, so I think that these two lectures will be enough for concluding the